PhD, yeah?
Yeah, I'm finishing
Yeah.
my PhD.
Doing the PhD in Hopkins University. Thank you for coming.
Yeah. First of all, thanks everyone for staying this late. To the last talk. So yeah, appreciate it. I'm a physicist and also an experimentalist, so this talk is going to be very different from the rest of the talks. But I'll try my best to connect the experimental measurements being done on this very interesting type of materials, namely topological insulators, to a beautiful mathematical ideas and theoretical predictions in this very physical systems. As like I've personally seen during this conference, mathematicians usually have very brilliant ideas to calculate something which they just want to calculate, not because they do exist in nature or in real materials, but then they find something very peculiar things like topological invariance, and then there are theoretical physicists who try to connect this brilliant ideas to real physical materials, but as we heard from Marcia, they don't often care about real experiments. So here we are, experimentalists who try their best to actually see those effects predicted in real and messy materials. So in today's talk, I'll be basically highlighting the recent advances in experimental measurements on topological insulators and magnetically doped topological insulators, where you can see the quantum anomalous Hall effect, so the quantum Hall effect but without applied magnetic field. So yeah. Before that, I just wanna show this first part, like the first passage from the famous Hall paper, the original Hall paper. So one like funny fact is he did that discovery at Johns Hopkins University, probably in the basement of one of the oldest buildings on our campus. So yeah, that's sometimes gives me a motivation to keep doing experiments because usually they fail, and then I like remember, oh, this guy somehow made this very famous measurement. Maybe so could I. And also this, I think Roland was at that time his advisor, and I think he's the very first physics PhD in the US, if I'm not mistaken. And until like 2 years ago, our department was named after him. It was named Roland Department of Physics and Astronomy. But then came a rich guy with 50 millions, and the department is now named after this rich guy, not this.
Exactly.
Okay.
The future.
Before I start my talk, I want to acknowledge all my collaborators. Peter Armitage is my advisor, who was supposed to be coming to this conference, but he had a change of plans and he asked for a replacement. And I'll be presenting on our work instead of him. And in our lab, we use optical measurements, and specifically in the terahertz range, to probe different types of quantum materials, which includes superconductors, different types of magnets, and topological insulators, which is the main focus of this conference. And I also want to acknowledge our collaborators from Hopkins University, namely Sean Ah and Kita Yi, for growing magnetically doped samples, where finally the quantized Hall effect was observed at high temperatures, which is just 2 Kelvin. But besides from that, they're also known for growing one of the best 3D topological insulators in the world, like this cell magnet. So yeah, and I want to thank our funding agency. Before I go to main experimental results, I want to give some experimental overview of the evolution of this field. So the striking evidence of this quantization in experimental measurement is well-known quantum Hall plateaus measured in 2D electron systems when the large magnetic field is applied. You can see these plateaus, and it turned out that those plateaus are not just random numbers, but they are actually quantized in terms of universal nature constants h and e squared. And and they don't depend on the non-universal things like carrier density, some material parameters, or anything. Just to appreciate this a little bit more, I just want to give a background on the classical Hall effect to build a foundation to whatever we'll be talking later. So in classical Hall effect, you just apply magnetic field. You have a basically piece of metal, and then you try to measure the you apply magnetic field applied here, and then you apply current, and then you try to measure the voltage just developed across this sample. And if you write a simple equations of motion for electron in magnetic field, and with some scattering or driving term, you can find this 2D matrix for a resistivity. And the off-diagonal elements will be corresponding to this Hall Hall resistivity, because you are applying the diagonal ones are longitudinal, and off-diagonal are Hall resistors. And in the classical limit, you never expect to be to have a perfect insulator, because you still have this resistivity. And the notion of this classical limit is that the Hall resistivity is never anywhere quantized. It's actually growing with field, and also depends on the material parameters like carrier density, scattering rate, mass, etc. So it's really remarkable from an experimental point of view that you can make these 2D insulators very clean, and then gap them, and then observe the behavior which is really different from this one. You have, instead of something which is growing with magnetic field, you see just plateaus, as in here. This is again those plateaus, and just so that people who don't experiment can appreciate it even more, I'm going to show the real Hall bar with how it's actually done. You can see how messy are those electrodes, and how and these samples, they never are perfectly clean. They always have disorder, but yet this plateaus are quantized to the level of 1 part in the 10 to the power of 10, which is ridiculously precise. So one can easily say that these systems are very robust against all sorts of disorder and experimental non-idealities, because you see there are a lot of those non-idealities. And also these plateaus are, since you see this phase transition here, those are different states of matter, and for condensed matter physicists, it remains a mystery as why these plateaus, they don't break any, they break exact, their symmetries are identical. So this plateau is breaking the exact same amount of symmetries as this one. And usually when you think of a phase transition, you always think about a symmetry breaking or unbreaking some symmetry. Because, for instance, when a material goes ferromagnetic, it breaks time reversal symmetry. When it goes superconductive, it breaks gauge invariance. So it remains mystery, why these are different states of matter, but yet they still have the same symmetries. And then comes Haldane, who basically told that there are topological aspects to these wave functions, and you can use he took inspiration from mathematics, basically. So if you place this 2D electron gas system in a periodic lattice, their wave functions are given in this particular form. Also, they are periodic. And if you actually treat those wave functions as a geometric objects in Hilbert space, to which experimental physicists are not used to, but you do it on a daily basis. But if you do it, it turns out that the conductance, Hall conductance, using Kubo formula is actually quantized in terms of E squared over H, and this value is called TK, and then invariant T is tauless. And there's the notion that it's quantized. It's analogous to to various topological invariants, which you guys calculate. I'm not proficient in them, but the only example I know is that this is similar to finding the number of holes in some surfaces, say donut versus a bowl. So those different plateaus are corresponding to this different number of holes, the genus of some surface, and those are different states of matter, and they cannot be adiabatically transformed from one to another. yeah, so this 2D electron gas system, you can realize this quantum Hall effect only if you apply magnetic field and break time reversal symmetry. And people then started thinking, can one actually break it without applying magnetic field, say with spin orbit coupling? And turned out it's possible. Yes, you can turn on the spin. You can make systems which have high spin orbit coupling, and then you will have this topological, edge states as in case of 2D electron gas, but without magnetic field. And it was first predicted for in 2D topological insulators by two different groups. Charles Kane, who was here early in this conference, they predicted it they predicted that graphene could host a so-called quantum spin Hall effect. But then it turned out that the value of that spin overtopping was too low to be realized in real experimental real material. But the other group, named Bernoulli, Cooks, and Zhang, they predicted that mercury telluride quantum holes could actually host it, and then it was experimentally verified 1 year later, as you see in this figure here. After that, people started thinking about 3D versions of them, and there were three groups which developed the math for the theory for the 3D topological insulators independently, and around 2007. And then first observation of this topologically protected surface space was done by David Shea in 2009. This is a RPES picture of the construct and the electron population here, and you can see this nice UF cone. And this is all good, but for experimentalists to actually verify that something is quantized or something is topologically protected, one should be able to measure their response function, not just looking at the band structure, but also try to measure something in the lab and see if it's actually giving what mathematicians and theoreticians have predicted them to give. So people started thinking about 3D topological insulators, and one of the ways to think about 3D topological insulators, which was developed again by few theoretical physics groups, namely one of them is Shucheng Zhang, is to think about 3D TIs as magnetoelectrics. Just to remind, magnetoelectrics are the types of materials which can develop a magnetization if you apply magnetic electric field, or develop a polarization if you apply a magnetic field. And usually this value is random for different materials. For instance, in this case, it's chromium oxide. It could be like 0 or very small number. But in case of TIs, they should be thought as a magnetoelectrics, which also give a quantized response. This alpha is not just a random number, but something which is quantized, and you'll be seeing in the next slide. So yeah, if you think of a thought experiment, you have a slab of a TI where the magnetic field is going outward on every surface, and you apply electric field. You would, if it was a perfect TI, you would expect that it will develop a circumferential current. But you can also think of this current as a bulk magnet in terms of bulk magnetization. And if you do this simple algebraic manipulations, you can find out that y component of this magnetization is equal to this electric field multiplied by this some constant. And in case of TI, it happens to be this very quantized value. And what is different from integer quantum Hall effect, which was observed in 2D electron gases, is this term 1/2. So it's not integer quantized; it's actually half integer quantized, but it has two surfaces. In terms of topological quantum field theory, this magnetoelectric effect can be thought as a addition to a Lagrangian, this specific term, and this it's also called E dot B type of magnetoelectric because it has this type of relation, and some of the materials actually have E cross B, but this specific type is E dot B. And also have this term theta, which we've heard a lot, is a axion angle, basically a and it's equal to, according to some symmetry consideration, it's constrained to be a integer times pi, and it's odd times integer, odd times pi for the topological insulators, and even number multiplied by pi for trivial insulators. And then, yeah, this is the detergent I was talking about on the first day. So this electrodynamics, the result of this Lagrangian results in electrodynamics, which is also known as axion electrodynamics. And the reason why it's called axion is that initially this term was, it was used to clear the CP violation in some interaction between quarks. That's why Wilczek, who wrote this paper, called it axion because it one sounded cool and also it cleared this problem, so it was called axion. But the consequence of this extra term in the Lagrangian is the modifications to a Maxwell equations. You see, these two have this now extra term, which is depends on theta. What I want you to pay attention to is that it has this delta gradient term here as well, which means that this effect is only observable at the interface between two media which have different indices, different axion angles. So which means that although we consider TIs to be just magnetic electrics, this formulation already gives you a effect of a surface state, because the only effect you're going to see in the TIs is going to be on the surface, and this gradient basically shows that. Okay, and so the next question is, what are the ways to measure this magnetoelectric effect in real experiment? And one of the ways to do it, as is highlighted in this paper, is to measure how the polarization of a light changes while it passes through this slab of topological insulator. And it was shown that, theoretically shown, that the Faraday rotations are going to be quantized in terms of fine structure constant alpha. And they're also going to be proportional to a sum of filling factor on top and bottom surfaces of the TI. So yeah, this was the motivation for the measurements which were done by our colleague, former colleague in our lab. But before, there's one slide right before that measurement. So there are some considerations. So to consider before actually measuring it. First of all, let's. So this is a typical density of state for Landau levels. So in real materials, they are not the delta function, but instead some sort of Gaussian distributed functions because of a disorder. So first of all, since we are probing with optics, we want to make sure that the probing frequency is not exciting electrons from one Landau level to another. That's very important. So probing frequency h times omega should be less or much less than this spacing in between Landau levels. And this in real materials, this already puts you in a frequency range which is almost 1,000 times smaller than the optical frequency. So 1 terahertz is basically, its wavelength is basically 300 microns, 0.3 millimeters. So it's 1,000 times longer than visible light. So which means that you cannot observe this effect with visible light. Another thing is sometimes this distribution of a single Landau level is super disordered because of all sort of impurities, and you also want to make sure that this spacing between the two adjacent Landau levels is actually larger than their widths, because if it's smaller, then you cannot tell them apart. Which sets some limitations on the magnetic field which should be applied to see this effect, because this delta E is actually directly proportional to D. It's equal to H times EB over M. So that is the second thing to think about. Taking all this into consideration, our former colleague measured the exact same thing. So what we do is we send the linearly polarized terahertz light, and then measure by how much its polarizations have been rotated after it passes through the 3DTI slab. And in here, we show this Faraday rotation as a function of frequency for 3 different samples, and those were 3 different composition of samples, which also correspond to 3 different filling factors on bottom and bottom and top surfaces. And as you can see here, at large enough magnetic fields, this response is getting quantized to these dashed lines, and these dashed lines are the quantized values for this rotation. And you can clearly see that there's a good match between the experimental data and the quantized value, which proves the theoretical expectation that in TIs, if you probe it with suitable frequency and you don't have too much disorder in your sample, you can actually see the quantized effect not only with electric probes, as it's done in Hall transport, but also with optics. So, also fun fact, turns out some insects have vision which is sensitive to the polarization of light. So if you were that insect, you will be actually able to see this effect of quantum Hall effect with your eyes. But yeah, unfortunately, we don't have that. But yeah, in theory, you could. When I said bismuth selenide, normally you just think this is just a slab of bismuth selenide and nothing else. But I just want to give you some sense of how people actually realize that thing, so that it's actually bismuth selenide. It has no surface disorders or anything else. So in this case, this same bismuth selenide which was measured, it's actually not just bismuth selenide grown on top of some dielectric substrate as sapphire in this case. It's actually have to be grown with caution, because usually you can't just grow material of type A on material B, because they usually have a lattice mismatch, and if there is a lattice mismatch, it will produce a strain, and you can never get a clean bismuth selenide grown. So you have to have this intermediate buffer layers, and they have to be insulating. And in this case, initially, few layers of indium selenide were grown, and indium selenide is just a trivial insulator. And then the next thing was to grow few layers of bismuth indium selenide, which could be both topological insulator actually and trivial insulator. I think Jet Pixley mentioned this transition in his talk a few days earlier. But in this case, it's all in insulating case, and only then you can grow high quality bismuth selenide stones, because now there's a good lattice matching, and you can actually have a clean bismuth selenide, and all of this is just insulating. So all of this was just done to get a good clean sample of bismuth selenide. And one question people usually have when they read about 3D topological insulators is this effect which you observed in 3D measurements the same as integer quantum Hall effect, which is observed in 2D electron system? The answer is no, and there are 2 main reasons. So first of all, 3D they have this non-chiral edge states which don't support any dissipationless transport. And in case of just a normal integer quantum Hall effect, you don't have this side edge, which is not gapped. The second, and I think it's even more important difference, is that in case of 3D TIs, you have this 1/2 offset, which is really important. So in case of integer quantum Hall effect, it's just E squared over H. In this case, it's 1/2 times E squared over H on top, and 1/2 times E squared over H on the bottom. And yeah, that's the main difference. And coming to the point about edge states, these edge states, they are, as I mentioned earlier, those are not gapped as this edge states because the magnetic field is not penetrating them in like perpendicular to them. So if you were to put probes on this 3D-TI and try to measure the whole conductance, you won't be able to do it with small magnetic fields because again, whenever you put the contacts, this non-chiral edge state, they may just short your like voltage measurements, and you won't be able to see any Hall effect unless you apply like gigantic magnetic field, which is in this case about 25 Tesla. And these measurements were done actually on the same sample as we did this Carrier rotation measurements. And the difference is that in optics, we were able to see the quantized effect at 7 Tesla, like even at 6 Tesla. But in DC transport, you have to go all the way to 20 Tesla to basically gap out those side edges. And that's the both feature of a 3D TI, but also a bug because you have to overcome it to see any sort of quantized effect. And the next question is like, I mentioned that this surface is like half quantized, and I think I was like asked during the conference, can you actually probe this, half quantization? Because every time we try to probe it, no matter if it's like optics or just transfer measurements, we always measure the sum of the bottom plus half plus bottom, which makes it like effectively just integer quantum half. So there's a way to measure it, and this is like an idea which we have, but we never implemented. I'm still working on it. So so this is a think of a thick single crystal of topological insulator, let's say bismuth selenide, and think of just a normal dielectric substrate, which is required in this case. So if we do just the measurement which I showed earlier, just send the light through and measure the rotation on this pulse, you'll just see the Faraday rotation, and that is going to be Faraday rotation on this surface, which is top, plus the Faraday rotation on this surface, which is bottom. But it's at the end of the day, it's still summing up to integer, not half integer. But if you look at the second pulse, which is goes all the way down to the surface of this dielectric, bounces back, and then bounces back from one of the surfaces, and then goes here. The total rotation is going to be Faraday rotation of top plus Faraday rotation of bottom. Nothing here because it's just normal insulator, and then one curve rotation, the polarization rotation at the reflection rate, and then one curve rotation at the fixed reflection. So if you take these two measurements and then like subtract one from another, you should be in principle able to like get this half quantized effect, unlike all other measurements which are just integer quantized. But this is very challenging because it's hard to grow thick crystals because it's sometimes it's hard to grow like thin films which are like 10 nanometers or 20 nanometers. In this case, it's going to be like half a millimeter. So there is experimental challenge to it, but in principle, those two could be distinguished, and if they are, then we can see a direct showcase of this notion of half quantization on the surfaces. And now I move to a intrinsic topological insulators, namely the ones which are doped as magnetic ions with magnetic materials, so that you can observe a quantum Hall effect even without magnetic field. So the idea is simple. The idea is simple. You have a normal 3D topological insulator, and if you dope it with magnetic impurities like chromium or vanadium atoms, you will open up a gap in the Dirac cone, and then if you are able to tune your chemical potential right across this gap, your response should be quantized, similar to a quantum Hall effect in 3D topological insulators. And then it was predicted by this group in 2010 that this could be in principle realized in chromium or iron doped bismuth selenide, bismuth telluride, and antimony telluride samples. And it took about 3 years to realize it in real materials. It was actually realized in chromium doped bismuth and antimony telluride. So none of this is actually a mix of those three. So it's realizing chromium doped bismuth and helium telluride, and here we show the Hall conductance, the hysteresis loop of Hall conductance as a function of applied magnetic field. As you can see, you can observe full quantization at even with just going to 0.2 Tesla, which is like incredible improvement compared to 5 Tesla or 20 Tesla. But one caveat is that these are all done at very low temperatures, which is 30 millikelvin, which makes it like almost practically not really accessible. And the reason was mainly attributed to a magnetic gap disorder. So I told that to open up the gap in the direct plane, you have to dope it with like ferromagnet, and like there's nothing wrong from the theory side, but when you try to implement it experimentally, when you try to dope it, you can never get a homogeneous doping of homogeneous placement of those chromium atoms, which leads to like some sort of gap distribution. And you can never get anything close to a Curie temperature of this material. Curie temperature of chromium, chromium. So Curie temperature is Curie temperature of chromium is almost 100 Kelvin, and we only see this effect until on 30 millikelvin. So people started to think about how to improve it, but another direction in which this field evolved was towards getting very precise resistance measurements. So this group in 2022 was able to grow a sample of magnetic TI, which shows a Hall resistivity accurate to a 10 parts per billion. So it's just, I think, 1 order of magnitude lower than the current standard set by graphene. So, but in graphene you have to apply magnetic field. And in this case, you just need, I think, like 0.1 Tesla. You just like, or you can do it even with like permanent magnet, which only supplies very small amount. So this makes it very practical. And I think in recent year in near future they will actually meet the resistance standards, and you can actually measure the ohms and everything with just what you measure from this magnetic TIs. But our collaborators from Rutgers, which I've mentioned in the very beginning of the talk, they were trying to battle this problem. So, namely the problem of low temperature at which this response is quantized. So they developed a new technique to engineer this structure of this different layers in this thin film. So basically, instead of just having a one layer of 3D TI doped with a magnetic impurity like chromium, they developed a so-called layer engineering. So they'll build different layers with different amounts of chromium, and then at the end of the day, they were able to reach the full quantization up to a temperature of 2 Kelvin, as you can see here, which is a quite big improvement from 50 millikelvins, which were done before, and this makes it like more practical to use because to get to those 30 millikelvins, you need really like dilution free, just which like not everyone has, which makes it like impractical. So after seeing this result in the normal DC Hall transport measurements, we decided to look at the optical response because there was a precedent that optical response was actually better than DC transport, as I've seen in case of bismuth selenide. We did that, and before I show the results on the magnetic case, I just want to like give theoreticians and mathematicians just some sense of how these measurements are done. Especially this optical measurement. So as I told earlier, you hit the slab of 3D topological insulator with a linearly polarized light, and then you measure by how much its polarizations have been rotated. And to do that, you first have to generate this light, which is done through this optical setup here. So basically, this emitter emits the linearly polarized light in here, and then it's like focused by different mirrors and lenses. And then we have a sample which is placed in the inside of a superconducting magnet cell because we have to apply large magnetic field. And after coming out of the sample, it's elliptically polarized, so we have to actually split the beam into x and y components so that we can like measure them separately, and then their ratio is going to give us this Faraday rotation. And just to give some idea how large are these rotations to quantum Hall effect, the Faraday rotation, which is equivalent to E squared over h, is about 3.5 milliradians, which is, I believe, is about 20 millidegrees. And the precision we have in the setup is 0.02 milliradian, which is almost like 1 millidegree. So we like absolutely have precision to be able to like measure this thing accurately. And that's what we did here. In here, I show the optical conductances measured at 3 different temperatures, 2 Kelvin, 5 Kelvin, and 10 Kelvin. And these are the hysteresis loops. So the black lines show the DC data from the like earlier work, and the color data shows a frequency response at different frequencies from 0.25 to like basically 1 terahertz. And what we see immediately is that the response is close to quantization, but not exactly. You can see this, and also the like coercive fields are also like slightly different. And if I do also look at this value as a function of temperature, we see that this hysteresis it survives until like 60 Kelvin, similar to DC, but we still have this offset. So we started questioning like why wouldn't we see this quantization in like optical measurements, although we saw it in case of piston selenide. And first thing we came across was the before that, yeah, I also want to show this. Here is shown the frequency dependence is shown in the color code, but if I actually plot it as a function of frequency, and here I'm showing both real and imaginary parts of Hall conductance. Real part, just to have some idea, real part corresponds to a non-dissipative part of the whole conductivity, and imaginary part is a dissipative part. And since we are measuring it with time domain technique, we can actually get both real and imaginary parts. But the real part is the one which is going to be, going to E squared over h, as in case of DC Hall conductance. So we see this frequency dependence, which is decreasing with frequency, as you can see here. And it was a little puzzling because in case of any most known theoretical models for this Hall conductance, we actually expected to see this sigma xy increase as frequency first and then decrease basically, which is quite the opposite in this case. So we started like
question.
Yeah.
Just want to understand how this optical conductivity is measured compared to the DC conductivity. What quantity do you measure?
Oh yeah, this sigma xy is it's extracted from Faraday rotation.
I see. What parameters do you need to do this conversion?
Yeah, I have them at the end of my slide. Let me yeah. I had them in the backup slide. So, first of all, we're talking about light matter interaction. So the proper basis is not XY basis, but right and left like polarized basis. So we measure this transmission matrix DXY, DXX, etc. We define right and left circularly polarized transmissions, and then from that we can get the conductances for right and left circularly polarized plates. And then if you do this transmission again back, you can actually extract the sigma xy.
Yeah, so I was wondering if there's some change in dielectric constant, etc. How would that affect the?
Oh yeah, it's important that you don't have anything like any sharp features in your spectra in the region where you're doing this. Actually, we have a phonon in this material, but it's at 1.6 terahertz or something, which is not at the low frequency part. So it doesn't really affect it. It's like flat until then. So yeah. Yeah. So we saw this dependence, which is in contradiction with most of the theories, and we started puzzling like why is that? And yeah, there are two questions: why it's not quantized, and also why the frequency dependence is like quite the opposite. And we like the very first thing we saw was actually this is the phenomenon which I was talking about. So this, here I'm showing the longitudinal conductance as a function of frequency, and as you can see, there's like very wide node at higher frequencies. And if you compare the bismuth selenide, which showed quantized effect, which is a 3D TI, which shows quantum Hall effect, this phenomenon is actually very like narrow. So what this like broadening tells us to spectroscopists is that there's like huge structural disorder in the system, and it's not surprising because we have so many layers of different dopings and different stoichiometric compositions. So yeah, this is one thing which was like apparent, but it shouldn't really affect the whole measurements because this is a like, longitudinal effect. But what was even more important is we came across this paper. So these guys here, they measured the gap, this magnetic gap. They measured the spatial fluctuations of this gap using STM. So this shows the distributions. Shows this magnetic gap in the Dirac cone as a function of x and y. As you can see, there is like a very large distribution, and this histogram actually displays the overall distribution of this gap. And compared to 3D TIs, where you can just apply magnetic field and have Landau levels, you just have one gap. But in this case, because of difficulties with doping with chromium, you can never get a single well-defined gap, and you will always have this very wide spatial fluctuation of the these gaps. And the range is actually very large. It starts all the way from like few milli electron volts to up to like 50 or even 60. So we've seen this work and decided, can we actually model our response to see if any kind of this disordered gap distribution can like fit our data. To do that, again, we started with a model which is very simple model which you expect for a whole conductance in a gap system. Yeah, this is very simple. And we were trying very different gap distributions, as in here, to see if we can match both real and imaginary parts of our data. And yeah, before like theoreticians will like say that, oh, this is wrong and you should use the mean field theory, I would say yes, you're right, but it's not so easy to use mean field theory. But yeah, we've come up with a distribution which can actually distribution of a single gap values, each of which have this sort of frequency dependence, and we fitted our data. And as you can see here, you can actually have a distribution which will like qualitatively describe all the features in the data. So you will still have a DC quantized effect in the DC limit, and it will have decreasing frequency dependence in real part and like increasing dependence on the imaginary part. So back to the point about mean field theory, the correct treatment would be to come up with some sort of mean field response. But as we saw here, usually mean field response in terms, especially when it applies to optics, it's going to be really dependent on the actual shapes and sizes of these small domains. So it's really not trivial just to run a simulation which would be true for all the samples, because if you grow another sample, you have slightly different. You might have the same like overall distribution, but spatial like shapes and spatial locations are going to be different. And mean field theory mean field theory would be giving you like totally different things. So yeah, that's why we just decided to do what we actually are capable of. We come up with a distribution of the gaps, and turns out it can explain all of the subtleties of our data, why it's not quantized, also why it has this frequency dependence, which is freezing. And yeah, mostly that's the reason why it's hard to get quantized response in anything but DC limit, because you have this very large gap distribution, which is I think would be addressed in near future by chemists who maybe will come up with a better way of doping the samples with chromium or other ferromagnets. And here I come to my conclusions. Today I talked about that 3D topological insulators are best described as a magnetoelectrics with a quantized response. And terahertz range is a suitable range because of the gaps between Landau levels. You cannot measure it with optics, but you can measure some with wavelengths, which is 1,000 times larger, which we do have. And magnetically doped TIs nowadays suffer from a large gap disorder, and that's why the temperatures at which they are observed are very low. And if this is resolved, you can theoretically go to all the way to like 100 kelvins, because the Curie temperature for chromium is 100 kelvin. And just a possible future application for like this, all sorts of topological insulators. There was a proposal which we also worked on, but don't have results yet. It was to use a surface states of a topological insulator in a waveguide geometry. So you would basically have your surface states here and here, and this is going to be your TI, and these are just trivial insulators which have even number of even number multiplied pi of axion angle. And then it was shown that because there is a magnetoelectric effect at the surfaces, if you make a dielectric slab waveguide out of them and then send the light in this direction, the modes, basically TE and TM, those are the guided modes in the waveguides, and the waveguides are systems which have dimensions much smaller than the wavelength of light. The coupling is going to be quantized here. This is the coupling between the modes, and then as you can see here, it only depends on the gradient of theta, which is again quantized. So in theory, you can use them for polarization control, like maybe in future applications. But this is something which we are also working on. But yeah, don't have the results yet. But yeah, the coupling between the modes also could be quantized, which is also just coming from this